Hi, hello from OpenStack. We're here to talk about a test and proof of concept we have done deploying object storage on an OpenPOWER hardware infrastructure. My name is Jacob Caspi. I'm a principal architect at the AT&T Domain 2.0. To my right is Tom Mathews, who is Distinguished Engineer of OpenPOWERs at IBM, and Christian Rice, who's the VP of Hyperscale at Canonical. I would like to take the time to actually thank IBM for providing us their lab in Austin to do all these testing, as well as Cindy Bilovitz on my team, my architecture team, who has spent many hours actually running the tests, but could not be here. So what is OpenPOWER?
So OpenPOWER is really a catalyst for innovation, a platform for innovation. It is an environment, this innovation environment that is from the chip up. What I mean by that is, down to the microprocessors, through the system, through the software, and it allows somebody to build an environment that is completely, 100% open in their environment. The other super important element of it is it's about collaboration of partners. So there's a large number of partners and participants in the OpenPOWER consortium. People building stuff at each level. Microprocessors, systems, firmware, middleware in the environment, and so forth, right? That's an important element of it. It's also about scale-out environments as well, cloud, HPC, analytics, and domestic IT elements that work well in a scale-out environment. And the other thing that it is the basis for our POC. We used OpenPOWER servers, specifically Power 8 servers, which have characteristics, industry-leading characteristics that are very advantageous in a Swift environment. They have more threads, we've got more cache, we've got more bandwidth in these boxes. So that's what OpenPOWER is.
So most people viewing this will probably be familiar with the Swift, but just as a little bit of a recap, it is an OpenStack project designed to do scalable storage solution. Objects files are written on multiple disk drives. They spread the data throughout those servers in the data center, therefore creating a redundant and high availability and high resiliency architecture. This storage is scalable. It's just by simply adding more servers, and if there's a server basically failure or drive failure, the data is built on other active nodes in the data center. Tom, could you please describe what the lab environment was?
Absolutely. So the lab environment involved 6 object store servers. The servers themselves were IBM OpenPOWER servers, specifically 822 LCs. In addition to the server environments, there were six Supermicro storage drawers in it. In terms of the configuration, we had a dedicated proxy server, and from a networking perspective, we used 10 gig data networks and 1 gig for the management network.
So why did we do this? AT&T is always very supportive of any open, either open source software or hardware, and looking for new ways and more cost-effective ways to do storage. As you can imagine, we have exabyte and exabytes worth of data and growing exponentially all the time. So we were looking for alternative ways to store data than we do now. And this this test allowed us to expand into a new hardware environment. So we were testing erasure coding on Swift, which allows us to have a higher efficiency of data storage to parity. We use distributed container sync for geo-replication, use various object sizes, and really the two things we were trying to verify is, one, there's a functionality compatibility, meaning all the functions that we are expected to see on an x86 platform actually works on the OpenPOWER. And then, of course, what is the performance levels that we got from the platform. So we varied the loads between small objects and large objects to see how much CPU utilization and resources are loaded on the computer or the header server. And basically, conclusion that we came up after doing very extensive testing is that even when we pushed something like 2,000 objects, the CPU was never tasked to the point that we needed to add more compute resources. And we also tested to see how much were the success rates, meaning success reads, meaning how often do we have to go back and do another reread. And as you can see, even at 1,100 workers, we still maintain almost the same level of success ratio. So in conclusion, the conclusion of the POC is that the hardware performed actually better than we expected and allow us to do a very efficient deployment of the object storage array. One of the other things I wanted to talk about is that even after we prove that this works on the hardware and the software, we still have to look at repeatable deployment, support, monitoring, sharing. So we have Christian from Canonical to talk about that topic.
Yeah, and I want to thank Jacob and Tom actually for inviting us in and helping us basically provide this substrate for us to put the software on it. I feel like AT&T and IBM here are driving the things that we feel are core to success in scale-out storage or private cloud in general, which are economics and choice. So looking at Swift as basically an industry standard open source software-defined storage solution for object storage is first like a really important step. We need to get big users like AT&T saying, yes, stamp of approval is given, Swift is good to go, we've used it in big configurations. And second, for IBM, just for driving the idea that we need to have multiple hardware platforms available that we can use to deploy. So for us, just for that opportunity for us has been great. Our story at Canonical is making cloud scale operations and deployment something which anybody can do. And so benchmarks are hard, and the reality is that every benchmark really only makes sense within your own context. So they've done testing here within their own lab, but we'd like to see others be able to drive that same testing and get the same level of confidence that Swift on their own hardware makes sense in order to be able to compare and do trade-offs. So what we deliver together with Ubuntu and with Swift is a set of tools that let anybody deploy Swift easily on any hardware, be it Power or x86 or ARM. And these are two components. The first component is Maz, which is basically a bare metal automation tool that abstracts bare metal away into an API. And with Maz, you can say, give me a machine with 24 cores and 64 gigs of RAM, and Maz will find one, will install the operating system from scratch, and give you back a running machine with their SSH credentials installed on that. And Maz basically takes away all the friction in getting the hardware deployed and up and running. And Juju is the second piece, which makes it so you can deploy any big software, of which Swift is a great example, because it's not just Swift you're deploying, it's the proxy, it's the object storage target, it's Keystone, and it's the glue to put those together. Juju helps you set that up without having to become an expert in any of those individual technologies. So essentially, what we're providing to you with Power, with Swift, is the ability to deploy this in a seamless manner, no friction, so that anyone can stand this up and run the benchmarks. And so you can do cool stuff like use BPF to get flame graphs going and so on. So anyway, the message here is that What AT&T and IBM are doing here is spectacular because they're really pushing the envelope and getting software-defined storage out there and bringing choice to hardware, which today is very much a monoculture. And we can only add to that by saying, this is available to anyone. Wherever you are, whatever hardware you have available today, you can basically set this up in exactly the same configuration as they have and run the benchmarks and see for yourself how well this works. So thanks very much, both of you.
Okay.